When we needed to know about subatomic particles, mass of an electron, mass of a proton, one of the major techniques that we used was accelerating the charged particle and then bending it in an electric field or a magnetic field, and that told us information about the mass to charge ratio, and ultimately we could figure out the mass. Now, what we're going to do now is use that same basic technique, that same principle, but apply that now to entire atoms and ultimately even to molecules. Again, the key here is that we have to first ionize them. In other words, we have to impart a charge on those particles in order for them to respond to the electric field. Let me quickly remind you about the Thomson tube experiment. This is a beam of electrons pointing directly at you. I can take a magnetic field. As I bring that magnetic field close to the beam, because the beam is charged and it's moving, you can see I'm deflecting that beam. And how much that beam is deflected, how much those particles are deflected, depends on how heavy they are and, again, what their charge is. So we're going to use that exact principle here in what's called a mass spectrometer. So let me walk you through how this works. Let's start out by looking at this pair of electrodes. I'm going to apply a high potential, high voltage again, across that pair of electrodes. And what's going to happen is it's going to generate an electron beam. So I'm going to generate high energy electrons. Unlike the Thomson tube experiment, I'm not interested in those electrons. I know all about electrons, but what they can do for me is give me a real high energy source of particles that I can collide with some sample that I'm interested in. Okay, so these are going to be now our little sledgehammer that we're going to whack whatever the sample is that we're interested in studying. So we're going to put in some kind of a gas, let's say, that we're interested in looking at the mass of. We're going to expose that gas to this electron beam, and that will cause general chaos, but in particular it will ionize a small sample, a small part of this gas, and make positive or negative ions. Now, if we then take accelerator plates, these are just metal plates, but we apply a potential across them, the ions that we generate here will be accelerated towards either the negative or the positive plate. If they're positive ions, they'll be attracted to the negative plate. If they're negative ions, they'll be attracted to the positive plate. So the ions start moving in different directions. We're going to be interested in the positive ions that we generate, and we're going to accelerate them. They'll accelerate towards the negative plate. Most of them will hit the plate and just die, but a few of them will make it through a small little slit that we're going to put in to this plate, and they will continue on beyond that plate. Now, what we've done is created a beam of positively charged ions that have essentially the same mass as the sample that we put in, but they're going to be missing one electron. But other than that, they will have, remember, the vast majority of the mass of an atom is in the nucleus, not in the electrons. So we've got our beam traveling here now. Now we're going to subject it to the magnetic field. Remember, the magnetic field is going to cause that beam of charged particles to bend, and how much they bend depends simply on how massive they are. My first car when I was a kid was a 1967 Opel Kadett, a little tiny car, and the big thing I remember about that car was on windy days I'd be pushed all over the road. The car would respond to the force due to wind much more than a very heavy car would. And that's the basic principle going on here, that the lighter particles will bend more in response to this magnetic field than the heavy particles will. If I imagine that I have two different kinds of atoms with different masses in this gas mixture here, well, if I adjust my magnetic field to just the right point that I can get, let's say, the heavier particles of these two different kinds of things that I have to just perfectly go through this little slit and then into the detector where I can measure them, then the light particles that I have will be, being light, will be bent more by the magnetic field, and so they will curve too much to be able to get into this slit, and so they'll land on this plate here and they won't be measured by the detector. Now, imagine if I change the magnetic field and I decrease the magnetic field so that I don't get as much bending. Now the heavy particles aren't going to be bent enough to make it into the detector, and if I adjust it just right, the lighter particles will then be just bent enough to get through the slit and into the detector. So I can use this adjusting of the magnetic field to select for one mass size or the other mass, just depending on, again, how I set my magnetic field. With a little bit of calculation, I can figure out what the mass of these two different types of particles is, as long as I make one crucial assumption, that the charge on the ions is 1 plus and not 2 plus or 3 plus or something else. And usually it turns out that the probability of knocking 2 electrons out is a lot more difficult than, or a lot lower probability than knocking only 1 electron out. And so that's a pretty safe assumption to be able to make that. So I can then determine the mass. And again, that's what I'm after. That's what this whole technique is about, figuring out accurately the mass of different atoms, or ultimately of collections of atoms in molecules. So let's consider then the other piece of this, which is just simply if I look at my detector as I change the magnetic field. Now I have just a little cartoon, but it's the same apparatus as I showed you before, just kind of more in a cartoon form. Here's my beam that I'm bending with a magnetic field, and let's suppose that I start out at a very low magnetic field so that my beam is not being bent enough to make it into the detector. Then I just slowly, gradually adjust my magnetic field and increase it until I reach just that perfect point where the beam is bent such that it goes right into the detector. At that point, I'm going to see a very large signal at my detector. I'm going to see a response current, a voltage come out of my detector that I can measure with a recorder. If I continue to increase the magnetic field, however, I will now be overshooting the detector. I'll be curving too much as I, again, continue to turn up my magnetic field, and so I'll miss the detector, and our signal will go back down to 0 again, no matter how far out we go. So at this particular position in the magnetic field, I know that my particle went into the detector. If I know my magnetic field, and I know what my electric field was, I can figure out what my mass of the particle had to be. And so I can determine the mass of all kinds of different atoms. So let's take as an example carbon. If I take a sample of carbon and I ionize it and I look only at the positive charged ions, and now remember, an ion is just simply removing an electron, in this case, from the carbon. So I have a +1 charged carbon because it's missing one of its electrons. That carbon ion will bend in the magnetic field. And what I find, interestingly enough, I get this big signal here corresponding to a mass consistent with 12 nucleons. Now, what I mean by that is protons and neutrons. I'll have a total of 12 of them corresponding to this mass. But I also find a signal out here at 13. So I have something here that is as heavy as 13 protons and neutrons combined, and then something that is 12. Now the interesting thing about these two particles is they're both carbon. They both are chemically identical, but they differ in mass. These two things are what we refer to as nuclear isotopes. They have the same number of protons, but they differ in the number of neutrons. And as we'll see, the number of protons is what determines the chemical nature of the atom, and in fact gives rise to its name. We call anything, in fact, with 6 protons carbon, but it doesn't make any difference whether it's a total mass of 12 or 13 protons and neutrons. So we'll say more on that in a short while. But the important thing right now is that they're different masses. They're the same chemically, and again, they differ in this case by 1 neutron, as it turns out. So again, those are isotopes. Now we can take this idea one step further, and instead of looking at an individual atom, look at an entire molecule, a collection of atoms bound together. So let's look at an example of an organic molecule called butane. This is a 4-carbon what's called a hydrocarbon. Butane lighters you're familiar with. This is the actual molecule in the fuel butane. And you'll notice it's got a total of 4 carbons and a total of 10 hydrogens all connected together. And if all of these carbons had a mass of 12 nucleons, which is what this guy has, and each one of these hydrogens has a mass of 1 nucleon. Then if I add those all together, I end up with 58. And indeed, I see a peak corresponding to this entire molecule now, but missing just 1 electron. So it has a +1 charge, it's an ion, and I see that entire butane ion come through, and I see a peak for it. Well, that tells me something really important. If I didn't know what this molecule was, it would tell me what the mass of this thing is. And that's telling me information about what it's actually made of. Now, in addition to that, I also see a fragment at 43, and that's going to turn out to be equal to the mass of this fragment, everything but this last CH3 group here. So that tells me some interesting information. That means somehow there's 15 units mass difference here between the entire molecule at 58 and this fragment, and so that gives me information about what that piece is. And I see something corresponding to this whole thing broken right in half. And then here's that 15 corresponding to just this fragment. So the important thing right now is not that you know or recognize what the fragments are. It's just that you recognize that when we bombard this sample with these high-speed electrons in a mass spectrometer, not only do we knock out electrons, but we can actually break the chemical bonds holding the molecule together. And by looking at the fragments that we get as a result, that tells us information about how the molecule is put together. In fact, this is such an advanced art now that we can tell, that scientists, not me, can tell sequencing for proteins, just massive, massive molecules, molecular weights in the tens of thousands, and the sequencing can be told simply by looking at the fragments coming off of these huge molecules. And that's used in immunology, and it's helped, in some cases, actually cure diseases. So it's an incredibly important modern technique, and helps us determine masses of atoms as well as masses of molecules. All with the fundamental principle that Thomson and people before him used, that charged particles respond to electric fields and are deflected. So our next step then is to take this information that we get from the mass spectrometer and look a little bit more closely at what the different types of atoms are in our environment.